Welcome, everyone. My name is Tim Deaver. I'm the Director of National Security Space Programs at Airbus Space and Defense Incorporated in Roswell, Virginia. First off, I want to take this opportunity to thank the Aerospace Corporation for the chance to be able to address this worldwide audience on optical communications and the advances we've seen in the last year. First off, I'm going to highlight some of the work we've done with the Aerospace Corporation, the Space and Missile Systems Center, through a cooperative research and development agreement, also known as a CRADA, supporting on how optical communications can better support the United States Air Force in its various missions. I'm also going to talk about the advances we've seen in inter-satellite optical communications capability, some of the challenges that go with that. I'm limited in what I can say because of proprietary information, but I'll do the best I can in that area. Then we're also going to look at some various vignettes on how optical communication can support not only the warfighter, but also commercial opportunities around the world. As I mentioned in my opening comments, I want to talk a little bit more about the ongoing activities we have at the Space and Missile Systems Center and the Aerospace Corporation in our CRADA that looks at how the Space Data Highway can support U.S. government missions in the future. We looked at the definitions and evaluations of different concepts of operations. We developed several use cases to include GEO to GEO, GEO to airborne, and even expanded into LEO to airborne. We looked at various levels of protection, the level of interoperability between lasercom terminals, as well as identified the security and resiliency requirements that would be needed of a system to support U.S. government military operations. From the Airbus perspective, we provided information on the network, some security architectures already in place, as well as plan to provide some airtime on the Space Data Highway network to facilitate testing for the Air Force in the future. Some of the joint activities we worked on together was what are the test metrics to validate operational capability and interoperability? Identified any critical risks that are associated with the laser SATCOM fielding and mitigations. There's always the concerns over eye safety and some of the other discussions we hear based on the various frequencies. Plan to do some additional testing in the future, and then conduct the technical comparison of the familiar RF SATCOM environment with the laser SATCOM environment of the future. From the Air Force perspective, they reviewed the Space Data Highway capabilities and design, looked at what the future capabilities are offering, and worked with us on some architectures for future spacecraft, as well as conducted a detailed analysis on the system features that enhance the security architecture, and that's one of the key areas of emphasis as we move forward and look at additional opportunities to cooperate on the CRADA. Let's take a look at some of the use cases that motivate us to look at optical communications to solve certain problems. One we're going to look at first is the airborne connectivity problem. Maybe not so much motivations needed there, but we're going to look at these because these are all well-known uses where higher speed, higher throughput, more secure communication methods can help us. From the risk of cyber attacks to risk of being intercepted to the need for increased data volume to export the data out of denied and contested areas, we see great potential for the optical satellite communications capabilities to do that. When we look at the use cases presented on the previous slide, we're frequently asked the question, what is the difference between laser satellite communications and RF satellite communications that are used traditionally and well embedded in capabilities today? The number one reason comes to mind is the jam resistance nature of a laser. It is very narrow in its beam width and hard to intercept or to jam by an adversary. When the laser beam is moving between the satellite and the user, it even becomes harder to jam because the adversary would have to maintain his position between the user and the satellite. One of the other advantages on a system like the Space Data Highway is that with proper encryption and controlled user interfaces, the network can be secure for several users at the same time or independent users well within their own confines and controlled within their own country and with their own citizens. And finally, laser satellite communication terminals are delivering data rates that were unheard of just a few years ago. With platforms like the Global Hawk and Gorgon Stare that used to take days to weeks to get their data exfiltrated out of a country, then we see the LEO constellations and high throughput constellations come along that reduce the latency to perhaps hours after a mission's complete. LaserCom, right off the platform, provides the ability to transmit that data in near real time, and as I said before, in record-breaking data rates. One of the more important advantages to me is the fact that we don't have to deal with the RF spectrum licensing through the ITU or other administrations around the world. The spectrum's becoming more and more crowded. There's less of it available for use, and there's always a challenge when we go to the ITU and the length of time it takes to get those permissions. And then also, it significantly reduces the chance of unintentional interference from other RF users. No great capability is without its challenges. As we look towards the lasercom terminals that enable laser satellite communications, size, weight, power, and cost, as well as manufacture, become a significant challenge if you're on a small platform. If you're on a large aircraft, a large geosynchronous spacecraft, even some of the large LEOs, we don't have to worry so much about the size, weight, and power. But when we're looking at constellation satellites, or we're looking at a small UAV, where every watt of power, every gram, maybe more likely kilogram of mass makes a significant difference. And then if we're going to produce these in numbers, taking 12 to 24 months to produce the optics for one optical terminal is just not going to meet the demand. Manufacturers and developers of lasercom terminals have put a lot of effort over the last few years into decreasing the size, weight, power, as well as the cost, and increasing the manufacturing capability for their specific optical terminal. One of the areas that has received a lot of focus on over the years is the interoperability between various manufacturers' laser communication terminals. We focus a lot on the frequency, whether they use 1550 or 1064, and within those frequencies, which channel are they tunable to, if there's only one, or more lately tunable across multiple frequencies, which makes them more interoperable with other manufacturers. We also look at the modulation schemes, the polarizations of each of the laser terminals, etc. But one of the areas that we often don't focus on is the compatibility of the position, acquisition, and tracking algorithms. When it comes to the pointing, acquisition, and tracking algorithm, one of the examples I frequently give is we have great vision with our two eyes. If we take and limit that by looking through a straw, and then we look around the room to find somebody else sitting across the room from us, it's pretty easy to still find them. Now, spin around a dizzy bat a couple times and try and follow the voice to try and find somebody. You can still do that as long as you're looking through the straw. Now, have the other person look through a straw also and not communicate with each other, and try and look at each other at the same time through the straws. You'll find that it's next to impossible. So there has to be some algorithm that's used between the two terminals when they're in space, or whether one's on the aircraft and the other's in space, of basic knowledge of where the other one is, but then also an algorithm to be able to start and locate each other, and then fine-tune that location to where they can lock on each other and start transferring data. The last challenge I'm going to talk about today is the compatibility between a host vehicle, be it via satellite or an aircraft, and the lasercom terminals, and the requirements that each impart on each other for stability. It's important to understand a lasercom terminal that's mounted on aircraft is going to have to be able to be pretty robust in its pointing algorithm and tracking to overcome the turbulence that the aircraft is also going to see. Likewise, there's various disturbances on a spacecraft also flying through space when its solar array panels adjust, or it does other minor maneuvers to maintain its orientation in space. To make sure that the laser communication terminal can withstand any of that jitter or bouncing around and still maintain track and continue to transmit data is really important to a solid design in a terminal. I wanted to take a little bit of time and just present some of the various vignettes that we looked at in our study. Real-time airborne ISR, we already covered that. We talked about the advantages that you get from having a UAV or manned aircraft connected via geosatellite back to a teleport outside of a conflict area. Just makes a lot of sense, enables a lot of capabilities, more jam resistance, and more secure. Connecting users in theater to capabilities and command and control centers outside of theater have been a big focus of a lot of programs within the last decade. The Air Combat Command and Control, Combat Cloud, JADC2 are a few examples of what's happening within the Department of Defense. And as we look at how SATCOM can enable that, but more importantly, optical SATCOM provides some more secure, higher data rate networks necessary to complete the connections for this growing and evolving capability. In the interest of time, I'm just going to talk about this one last vignette that we looked at in the study, the remote sensing satellite data backhaul capability. Even though this capability has been around for a decade, it's getting more attention. More and more people are realizing the benefits of being able to see in near real time or real time, not only the imagery coming off the remote sensing, but also to be able to task in near real time. And this is done through the intersatellite optical links that are both present on the LEO spacecraft as well as the GEO spacecraft. Increased volume of information, data rates. We're not waiting hours or days to see the images that were taken over the horizon. Pole-to-pole coverage when you use a geo satellite, so you don't have the frequent outage periods you get with ground communications. One of the underrated advantages of offloading data off of a remote sensing satellite more frequently and with longer contact windows is frequently the design capability of the satellite is limited by its data storage, its ability to downlink the data through infrequent ground contacts, and other parameters that are removed with laser satellite communications. I can do wider field of views, I can image longer, I can do higher resolution. All those capabilities are enabled by the fact that you have laser communication terminals on board your satellite. As I reach the end of my time today, there's a couple other use cases I want to briefly talk about that apply themselves well to space-based lasers. One is communications among the constellation satellites we see blossoming throughout the world. Being able to communicate from one satellite to another in RF, we talked about those problems before, so when we move to optical, a lot of those problems are overcome. DARPA and the Space Development Agency are leading efforts on interoperability and have funded several experiments that will be launched next year to be able to validate the interoperability between various vendors' lasercom terminals, as well as the pointing and acquisition and tracking algorithms within their own capabilities. As we look forward to taking the first woman and returning man back to the moon and establishing outposts on the lunar surface, as well as in deep space, concepts are evolving for how those communications capabilities can be enabled by lasers communications. There are many other use cases that we looked at, but in the interest of time, we'll conclude there, and I thank you for your time. It's been pretty amazing watching the advances in space-based optical communications over the last decade. The speed in which things are changing has just been truly amazing. From increased data rates, decreased size, weight, and power, the willingness of various vendors to establish interoperability norms, joining at the Naval Research Laboratory to bring those norms to realization and ensuring their use before we go space-borne. There are many other use cases we could have shown today that show how optical communications can help overcome current issues for operations in denied or contested areas, as well as you let your imagination go. But in the interest of time, I truncated it to the ones that I thought were more interesting and relevant to the time we had today. And I thank you for your time.